Okay, so welcome to day 10 of Math 331 problem solving. I hope you had a better weekend than the tripod swivel interface system. It seems to be extremely slow and lethargic today. So I hope you can show an energetic class so that it will be inspired to start moving at appropriate speeds. So there's lots of different topics to do in problem solving. We should do some geometry. Okay, and then could one of you close the door? I feel if I move over there, I will never get the camera to focus back on me today. Thank you. And so what I want to do is I want to talk a little bit about a Putnam problem. I specifically did not tell you which Putnam problem. Now, you could probably Google it, and there's a good chance you could figure it out. If you know the difficulty of the problem, that often affects how you attack it. Sometimes in a good way. Sometimes in a bad way that you feel like, oh, this can't be done. Have you heard the story of the Stanford grad student who solved the open problems because he didn't know they were open problems? He was either late to class or daydreaming and didn't realize the professor had written on the board a list of the most important open problems in the subject. And a week or two later, he goes to the professor and goes, it was much worse than normal. I was only able to get 2 of them this week. Okay. And the professor, being a professor, just puts it in the pile of all the stuff to do on the desk and promises to get to it at some point. And then very excitedly contacts the student, a week or two later, oh my God! We got to get this written up and submitted fast. You just solved. And so if people want more details, I'll provide more details about this. It's one of the most entertaining stories. There's lots of different variants of it. He did not know they were open problems when he was attacking. And that put him in a very different mindset. And so if you know this is a Putnam B6, you're going to look at it very differently than if it's a Putnam B1. Okay. In all fairness, I actually don't remember which Putnam one this is. So the problem was the following. Given 5 points on a sphere, show there exists a closed hemisphere containing at least 4 points. At least 4 of the 5. Is it possible the closed hemisphere could contain all of them? Sure. Do the points need to be distinct? Yes.
Well, if they are not distinct, it's arbitrary. I mean, it's pretty straightforward. It's like they're obviously all in the same hemisphere, right?
So what if you have 1 point doubled, 1 point tripled? You say 2 points on the north, 3 points on the south.
I think it still works.
You can still get it like that, right? So this, you don't have to go southern hemisphere and northern hemisphere just because I'm giving you those words as the clues. You can go, let's take the eastern hemisphere or the western hemisphere. So it probably would still be true even in the limit. It might be easier to assume that they're distinct. So maybe for now, I'll assume 5 distinct. And we'll see if we actually really need that assumption. Okay. I don't particularly care about this problem, but I care about the thought process as to how you attack this. What should our first step be? How should we start attacking something like this? Yeah.
Actually, well, I thought that this problem was very pigeonhole-like.
Good. So the pigeonhole or the box principle, you often put Dirichlet's name on it. So that's going to be one of the main units for this week, is the box principle, Dirichlet's pigeonhole. This is something we haven't done yet, but when you start hitting things like at least 4 out of 5, things like this does suggest a pigeonhole argument. So good. This is one thought you should have. And the way it's really going on is, I have many different closed hemispheres. I want to have at least 4 points in one of them. So I'll say what the pigeonhole principle is in a little bit. There's another thought you should have in attacking this problem. And to discuss point 2 is the entire reason why I want to do this problem. So what should your thought be when you're looking at this? Excellent. What goes on in 2D, in 1D, in 4D? Right? I'm giving you a problem in isolation, but I really shouldn't look at it as a problem in isolation. Build intuition from smaller sets. Build intuition from smaller problems, and then attack it. And then to impress people, you throw away the smaller dimension ones and just submit the solution for, the three-dimensional problem that the Putnam people ask you for. But there's nothing that says you can't look at a lower dimensional case first. If only they gave you hours and hours and hours. Oh, they do give you hours and hours and hours on a Putnam. Wonderful. Right? You've got 6 hours. Plenty of time. So spend some time trying to think of lower dimensions. Whenever you see a problem, you also want to ask, why these numbers? So 4 out of 5. How do we interpret 4 out of 5? For like Star Trek Voyager here. How should we interpret 4 out of 5? What would be your guess for 2D? And there's a lot of guesses that work. I've given you one data point. Unless you're in economics, this is not enough to determine what's going on. What might you guess for 2 dimensions? In 3 dimensions, it's 4 out of 5 points. What might you guess in 2 dimensions?
Well, you can do both different dimensions and different, number of points.
Right.
Wrote down so you can
Right. So if I want to go down a dimension, I probably have to lower 4 and 5. What do you think I should lower 4 to? What do you think I should lower 5 to? And there's a lot of possibilities. We have one data point. All right, let's lower all the way down to 1 dimension. Okay, so let's start off in 1 dimension. All right, so what does a circle, we might as well assume it's a unit circle. What does a unit circle look like in 1 dimension? All right, let's go to 2 dimensions. So if you have a really good imagination, that's a circle. Okay? That's the 2-dimensional circle. And we have to choose some number of points, and at least some other number of points must be on a half circle. What does the circle look like in 1 dimension? Yeah, but actually it's a disconnected segment. This is the 1-dimensional circle. If we had the filled-in disk, we would have the interior here, and we would have the interior of the segment. This is the 1-dimensional version of the problem. All right, so how many points can we add and make sure that we have a certain number of points in the same half circle? The half circles are not that bad in 1 dimension, right? How many half circles do we have? So what are the only half circles we have in 1 dimension? Each point. So this is a half circle, and this is a half circle. We have 2 half circles. How many points can we throw down to get a certain number in a half circle? Well, I could put my first point here. I could be problematic, and I put my second point here. And now for my third point, I have no choice. I have to put it back in one of my 2 half circles. So let's say over here. So in 1 dimension, it's not that hard to show if have 3 points, at least 2 in the same half circle. Maybe it's a little bit inappropriate to be calling this a half circle. We have hyperplanes. Maybe call it a subcircle. You get it a little bit lower because it's not really a full circle. I don't know. Anybody have a better word other than the opposite of hyper? Lethargic? What do you want, lethargic or sub? Sub. All right. So we have to have at least 2 points on the same subcircle. Okay, so let's look at our data. So we have the dimension, number given, number on the half. Dimensions 1, 2, 3. We know if you're given 3 points, you have 2. We're going to assume whoever gave us the problem knows what they're doing. Not always a good assumption. So again, we do not have many classes at Williams where we can afford to do this, where we can take this much time and really talk about the thought process and not be running to get to theorems. We're not going to prove that many theorems this semester. I was actually talking to somebody proudly about this fact yesterday. This is really talking about how would you analyze something. Any thoughts what should go in the missing slots? 4. Not that I don't have any confidence in you, but... And what else? 3. I'm just trying to fill up a whole lecture. Okay, so 4 and 3. And again, if we just looked at one data point, the 5 and 4, it's not really clear what we should be doing in 2 dimensions. Maybe the 4 is 1 more than 3, because we're in 3 dimensions. Maybe it's 1 less than the dimension squared, and this is always 1 more than that. There's lots of different ways you can get the number 4. But now that we have this pattern, it seems pretty clear what's going on. So now let's try to look at what's going on in 2 dimensions. How many of you have seen Dirichlet's pigeonhole principle before? Or the box principle? Okay. So, okay, the camera's actually waking up and moving better. Excellent. So I think all the class participation has helped. Okay. So the box principle is one of the most important principles in mathematics. So Dirichlet, box, pigeonhole principle. So this is used not just to prove results in problem solving, but actually prove theorems we care about. And what I might do is I might actually do a little bit of number theory later this week and actually show you why you could use this to prove great results. I'll hold off on that now. I will resist the temptation, which is hard as a number theorist, and just talk about this. So the way it works is the following. You start off with n boxes. 1, 2, 3, 4. And you have, I could probably get into trouble with this, you have a person with a pigeon gun. Anybody here seen Despicable Me? Okay, so in Despicable Me, what kind of, okay, good. What kind of gun does the person have?
Which film?
Despicable Me, not the sequel. The first one, which is now the second one in the series because the third one, Minions, takes place chronologically earlier. There's the jelly in Minions, which is, no, I'm sorry, there's the jelly in Despicable Me 2. There is the jelly gun, yes. But in the first one, what kind of gun do they have? Not Gru, Gru's nemesis. The oh yeah guy. It's something from the ocean. The squid gun, right? He has a gun that shoots squids. So, given that we have this in pop culture, having a gun that shoots pigeons doesn't seem to be that inappropriate anymore. When I was growing up, so we have the pigeon gun. But this way, when I talk to my kids about what I did today, I can talk to them about Despicable Me and they will enjoy it. So what you do is you load the pigeons into the gun, and then you shoot the pigeons into the boxes. Oh, this should be n minus 1 and n. And we have n plus 1 pigeons. And when you shoot, each pigeon has to go into one and only one box. What can you tell me after the n+1 pigeons are shot?
At least two are in the same box.
Good. So shoot n+1 pigeons into n boxes. Therefore, at least one box has at least two pigeons. And the reason is, what's the average number of pigeons per box? It's a little bit over 1. If every box had 1 or 0 pigeons, the total number of pigeons accounted for would be at most n. So at least one box must be average. Another way of looking at it is, you cannot have a class where everybody is below average. Can you have a class where everybody is average? Yes. You've actually seen this in a calculus class. Where have you seen this in calculus? The mean value theorem. If you look at your average speed in the interval, if your speed is continuous, there must be at least one point where you're traveling at your average speed. If you always travel below your average speed, how could this be your average? If you're always traveling above your average speed, how could this be your average? So there must be at least one point in time where you're traveling at your average speed. The mean value theorem is extremely useful in calculus. This is one of the easiest ways to prove the fundamental theorem of calculus if you assume your function is also differentiable, continuously differentiable. All right, so we're all comfortable with Dirichlet's pigeonhole principle. So now let's start applying this to the two-dimensional case. Okay, so where should the first pigeon go? I'm sorry, the first point go? It can be anywhere in the circle. Any preferences? Yeah.
Very top one.
Yeah, I would tend to point it over here. There are some people who would put it over here on the right. I think those are both defensible choices. Down here is just wrong. I actually have a great map, an upside-down map of the world, where they actually flip it, and it's really interesting looking at how your orientation changes when you see something like that. Normally people do North Pole or far right. Doesn't really matter. We have freedom in terms of where we put the first point. What about the second point? Remember, we're trying to show that there must be at least 3 points. So where should we put the second point? Now we have a little difficulty. So we can start doing things by symmetry. We could say, well, look, without loss of generality, it's somewhere on the right-hand side at an angle theta. Or the other possibility we could do is we could say, well, look, we've got 2 points. Let's have the North Pole right between the two of them and have them symmetric about the North Pole. So you have some freedom. So it might seem like this is the best way to start, but I might actually like choosing the North Pole to be symmetric about those 2 points. You have some freedom. And then what can we say about the angle between them? Well, it's at most 180. Because if it was all the way down here, we would just flip it up. So you always want to use symmetry to reduce, reduce, reduce. So out of curiosity, did anybody try doing the two-dimensional circle? Okay. Yeah. So now we have 2 points. And we know these 2 points are close to each other. In order to win, we just need to show that there's 3 points. So how could we win? Where could we place the third point and win? There are some regions that are clear wins, and then there's some regions which are wins but require a small amount of work.
Well, the only place you could put it where the only area you could put it and not win would be the reflection of the area between.
Good. So this is a clear win between these 2 points. But actually, if we draw the line from here through the center, anything in this part is a win. Conversely, if we draw the line from here to the center, anything in there is a win. So big win is here, win is here, and win is here. So down here is where things are troublesome. How many points do we have to place down here? 2. So somehow 2 points, or 2 pigeons, must come in here somewhere. Because we have to put down, we're trying to put down 4 points. Well, if we put down 2 points here, then they can team up with this one and we win, or they can team up with this one and they win. And so this is the proof that you can do 3 points out of 4 in the same hemisphere. So we can now actually fill this in. So the idea was to try to figure out regions. How do we put down the points so that we can methodically go through all the possibilities? Do we think that it's possible if we have 5 points that we could get 4 of them together? It doesn't ask for that. But maybe what's going on is there's a really nice simple proof that shows you can do 3 out of 4. Could we do 4 out of 5 in 2 dimensions? Well, if we could do 4 out of 5 in 2 dimensions, what might you also ask? Yeah, in 1 dimension, could we do 3 out of 4? Well, 1 dimension is much easier to analyze. You know, if we go back to 1 dimension, I could go 1, 2, 3, 4. And I'll clearly have trouble. So the question is, can we set things up in 2 dimensions so that we can't do 4 out of 5? Yeah, so I was wondering, would a pentagon work? If we have 1, 2, 3, 4, 5. You know, they say the camera adds 10 pounds. It also adds 10 degrees on all angles. Any Friends fans here? The quote, how many cameras were on you that day? Okay, so this is supposed to be a pentagon. Would we have 4 of them together? So let's think about what are the angles here? Each angle is it 72? So this is 72, this is 72. To get to here, it's going to be more than 180. So we will not be able to get. So we are doing a lot more than the problem asks. Not only are we showing that you can do 3 out of 4 in 2 dimensions, but they don't even ask us about 2 dimensions, we're showing that this is the best possible. That there is a configuration of 5 points where you will only have 3. What do you think might be the next natural question to ask in 2 dimensions?
What other configurations?
So classify all configurations where you will not have 4 together. So this becomes a classification problem. Now I can perturb a pentagon just a little bit. So can I have some things that are fundamentally different? Could I have points that are really close? So that's one possibility, is to look at all the ways with 5 points I can only get 3. What other question could we ask?
In general, if we're given n points, how many can we?
Great. So as a function of the number of points given, how many points are guaranteed to be on a hemisphere or a semicircle? Or the next one might be, if I want to have a guarantee 4 points are on the same semicircle, how many points do I need in 2 dimensions to guarantee that? Is it possible? Well, it seems like if I keep increasing the number of points here, eventually I should be able to guarantee 4 are on. So that could be a nice problem. And it could be a really crappy bound. So for instance, maybe to guarantee that there are 4 points, if I have 2017 factorial squared points, I'm guaranteed to have at least 4 in the same semicircle. This is almost surely overkill. But how many points needed in 2 dimensions to ensure at least 4 in same semicircle? That's a great question. Do you think the number is finite? Yeah. And if I replaced 4 with m, do you think it's finite for that as well? Probably. So maybe there's an easy proof to show that it's finite. And then the question is, of course, what's the best result you can do? Yes?
I feel like it has to do something. It has to do with the even or oddness of the given number of points.
Okay.
So, for example, in the 1-dimension case, we have 2 boxes.
Right.
So we can, for all odd numbers,
Right.
we can ensure that like for all odd numbers,
Mhm.
given we can ensure that m minus 1. No.
No, you'd be having like a half
Yeah.
thing. So again, we also have to be careful that maybe 1 dimension is special. Because there really are only 2 hemispheres, and maybe, or I'm sorry, we're calling them subcircles. And that maybe we don't have enough things to free and move around. So one of my favorite examples is in calculus. One of the big things we do in Green's theorem is we talk about integrals over closed curves. In 1 dimension, how many closed curves are there? So essentially in calculus, how many closed curves are there in 1 dimension? So what does it mean to be a closed curve? Anybody know the definition of a closed curve? So you start and end at the same point. So in 1 dimension, if I want a closed curve, I have to start and end at the same point. Essentially, I can go out and I can come back. When you integrate, if you go in the opposite direction, the integral is now the negative of what it was before. So what is the integral of a function over a closed curve in 1 dimension? 0. This is not an exciting theorem. The 1-dimensional Green's theorem is boring. Because the only closed path that exists is out, in. In 2 dimensions, I can walk around this table. We'll see if it actually works. Oh, wow, it's working. Let's see, does it track back? I don't know. So I just emerged from nowhere. Okay, so in 2 dimensions, you can walk around a table. You can have a lot of closed paths. Green's theorem becomes interesting in 2 dimensions. So when we're looking at stuff like this, I do like looking at lower dimensions, but I'm sometimes worried that maybe the lower dimensions is not giving me the true picture of what's going on, or maybe it does for some things but not others. Okay. Are we happy to move on to 3 dimensions, or do we want to talk more about 2 dimensions? This is your class. Yes.
One thing
Yes.
to two-dimension. So if we have two if we have 2 m points.
Okay.
So if we fix one of them on the circle, and we draw a diameter from it across.
Okay, so what you're basically saying is if we do something like this, if we take 1 point over here,
Yeah. So
points have to be on either side.
2 boxes. So I feel like we can.
So if we want to get at least m, maybe we start with 2m plus 1, or maybe 1 plus maybe 2m minus 1, maybe something like that. We start off with 1 point here. And then for every subsequent point, it's either in the left or the right.
So in 2 dimensions, it'd be 7 points to guarantee 4.
You got to be very careful how you phrase it. In 2 dimensions, 7 points guarantees, but that doesn't mean 7 points is the smallest number that could do it. It might be possible to do it with 6. Because here, you are choosing ahead of time which 2 hemispheres are under consideration. The problem allows us to use, semicircles. The problem allows us to use any semicircle. So for instance, if we start clustering a lot of points up here, don't go east-west, go north-south. So we know that 7 would be an upper bound. It might be possible to do it in far less than 7, like 6. But this tells you already that it's finite. Another way to do it would be, I think if you looked at the average spacing between the points in radians, right? If we have n points, then the average spacing should be something like 2 pi over n. And so there should be a certain number of points that have to be close relative to the average spacing. And you have to be a little bit careful. This is a far more elegant way, so please make sure you email me. So,
yeah, I think if we make an amendment,
okay.
if we start with 2 times m plus m minus 1, it should work.
Well, this is 2m minus 1.
Oh, yeah, but without the plus 1.
Oh, you don't need the extra 1.
I don't think so.
Probably not, because for the last point, once you put it on, you're fine. It's got to be on one side. So we might even, again, if we can do that, so let's say this is our first point. Then our second point, third, fourth, fifth, sixth has to go somewhere. So this is enough to show that 6 points would do it. So I think you're right, we don't need the plus 1. And in fact, now we don't even have to worry about investigating the case of 6. So if we want 4 points, we're fine with 6. And now the question is, now that we have a conjecture like this, can you actually prove it? Can you prove that maybe, and again, I'm not saying that this is the right conjecture. Here's an upper bound. Does this bound, is this optimal? If I give you 2m minus 3 points, is there a way to configure it so that I do not have m minus 1? What shape would you try looking at? So if you're trying to find a counterexample, what shape might you try? Yeah, try a 2m minus 3 regular gon. Or probably you would phrase it as a regular 2m minus 3 gon. So see what you do. That would be a really easy check to see. And then we might actually have just proven a little result. A really, really good friend of mine is the problem editor of the Pi Mu Epsilon journal. I strongly suggest that you check and see if this is right and submit it to me, and I will pass it on to my friend. And if this is new, this could be a nice publication or a really nice challenge problem. So all we have to do is we checked very easily with the pentagon as to what the angles were. If the angles are right over here, this could be enough to win. It's a calculation that needs to be done, but it's not that hard of a calculation. Do people want to do it right now and just find out? All right. So we have to do 360 divided by 2m minus 3. So you've got to figure out what's the right way to do this calculation. So that's how much each angle is. And for the pentagon, to get 4 points was 3 angles, right? So to get m points is m minus 1 angles. So the angular girth, measurement, but girth is easier to write, would be 360 divided by 2m minus 3 times m minus 1. m minus 1 is greater than 2m minus 2 over 2. It's greater than half of that. So this is greater than 180. So this proves that there's a configuration with 2m minus 3 points that doesn't work. And, crap. I'm now a liar. We actually did prove a theorem today. Right? This is a theorem. Right? The minimal number of points needed on a circle to ensure M are on a common semicircle is 2m minus 2. So I have no idea if this is new. How should we figure out if this is new? Look it up. How do we look it up? This is the 21st century. How do we look something up? Yeah, Google, put in some kind of search engine. I am embarrassingly old enough, I still remember the day in grad school when someone told me there's this new site called Google that you got to look at. Or they might have said new search engine back then, not new site. But yeah, let's look this up. Let's see if anybody's ever isolated this as a result. Would you be surprised if somebody else has isolated this? No. This seems like a very natural thing that someone could isolate. I don't care. Had any of you seen this before today? Wonderful. So just in terms of investigating a problem, we try to put it in a bigger picture, ask some natural questions, and from that came up with a nice theorem and a nice complete classification. What was great is looking at the case with 5 points gave us a wonderful counterexample. And then, well, let's just hope that that counterexample generalizes. Hey, good, it does. So we don't have to be clever now and search for other things. So you can see that there is symmetry up the wazoo on this problem. So this is not how I was expecting today's lecture to go, which is absolutely fine. We're not in a rush. This is, I think, a much better use of time than what I was going to do. I'll just do that part on Wednesday. Okay, wonderful. So I'm very glad we did this. We've got our theorem now. So now since this is a theorem, I should put a QED box somewhere. Okay, excellent. All right. So I think we've now completely resolved the two-dimensional case. The one-dimensional case we've completely resolved. Whether or not anybody's completely resolved the three-dimension, I don't know. But we'll do some Googling later. That's now a verb. And now we'll try to figure out, can we actually solve the original problem, that we were supposed to be doing? But in mathematics, often when you do research, things get frustrating and you can't prove what you want. So what you do is you change it to what can you prove? And you change your question. And just sometimes you don't necessarily, sometimes you might report, this problem was motivated by a search for blah, couldn't do that, but we are able to prove the following, which is of interest. All right, so now let's do 3 dimensions. So we have a sphere. Show 4 of 5 on a common hemisphere. Okay. I debated using the data projector, but the data projector means I have to use the high-quality camera recording. This is probably one of the few times that there will be a small decrease in your classroom experience because I'm recording my lectures. You're going to have to watch me draw even more figures. I will try to draw a good sphere. All right, and then so hopefully this kind of looks like a sphere coming out of the board at you. In an emergency, if this is really bad, I do have a basketball in my office that I can bring down. But hopefully this is good enough. We need to generalize what we did before. Where should we put our first point? Or do we want to do our first 2 points? I liked the first 2 points. So where do you want the first 2 points? Yeah, which circumference do we want to do?
Like the main one.
Yeah, which is the main one? This one or the big one?
So anyone that passes, anyone where you could draw the circle that passes through those 2 points in the center of the sphere.
Well, but I can do that on any one.
So
It's which is going to look best on a three-dimensional blackboard by a professor who is artistically challenged. Yeah, the big outside one, right? You know, don't challenge me too much with my drawing. 2 ones like that. And then we do have the point in the center over here. I'll do it, C for center. And now these 3 points will form a cross section cutting through. Now we need to add a couple more points, right? So we want to figure out where do we want to put all the other points. Because at this point we're now starting to lose symmetry. I can put on 2 points here and I can rotate. But in terms of the angles that the third one makes, I don't really think I have that much freedom. Can I assume that there's a third point somehow between these 2 coming down? Maybe not on the midway point, but maybe somewhere. So this is where it gets painful in terms of talking about how you would draw and talk. But what we did back, let's see if the camera will follow me and go back to the one-dimensional case. All right, no, one-dimensional is so boring it's not worthwhile. Let's go back to the two-dimension. We took this, drew a line through the center, and we already had 2 points here. So we got 1 more point in there, we would win. And we did this one over here. If we got 1 more in here, we would win. So we had to have 2 of them down here, and with both of them down there, that fixed that. So we are trying to get 4 points together. We've already got 2. We have to add 3 more. If 1 point is close to those 2, we're already in really good shape. Yes?
Can I just clarify? The way you've drawn it now, you're sort of bisecting the sphere into the part that comes out of the board and the part that goes into the board, right?
Well, this is the great circle.
Yeah.
And then this is the hemisphere coming out. So I can always assume that these 2 are on, say, the, let's choose our coordinate axes. Maybe this is x-axis, this is the y-axis, and this is the z-axis. And this will obey the right-hand screw. So x is coming out of the plane. So these 2 are both in the x equals 0 plane.
Okay.
I can always rotate them to be in the x equals 0 plane, and then I can spin it so that they are on equal sides of the z-axis.
But then I guess no matter how you draw your first 2 points, there'll always be a member of either, like in this case, for example, you could say that these 2 points are a member of the hemisphere coming out and also the hemisphere.
Correct. Oh, they're members of many hemispheres. So they will be on the members of the hemisphere coming out, the hemisphere going in, the northern hemisphere, as well as lots of other ones where I can basically just take this like a shell and rotate it. So they are on many different hemispheres right now.
I think if you consider the case where you're dividing the sphere into 2 hemispheres, one of which is going out, one of which is going in, couldn't you just pigeonhole
Good.
the rest?
Well, what I know is I've got 5 points. If I look at northern hemisphere and southern hemisphere, what must be true about one of those hemispheres?
It has 3 points.
One of them has to have 3 points. So I can assume that there's 3 points on the northern hemisphere. If I want, I can assume the first 2 points are here, but then my third one I have to put somehow arbitrarily. I can always, if I want to assume it's on the right side. But I know by pigeonhole, at least 3 in northern hemisphere. And in fact, if there were 4 in the northern hemisphere, we'd be done. So we would also now know if not 2 in south, done. So now we know we have 3 things up here. And we have 2 more points to add. So we can start playing the same game in terms of this is going to cut us up into a sphere, and we will have the, I guess you want to call this the coming out sphere and the going in sphere, hemisphere.
Sure.
So one of them already has a point. Or another way of looking at it, and this is similar to what we had before, we've got 2 points here. We've got to put down 3 more. And we have outer hemisphere, inner hemisphere, outer hemisphere. Okay, one of them has to get 2 points. So this is like a double pigeonhole. So you have outer hemisphere, have inner hemisphere. I think it's actually better not to initially put that 3rd point in. And we know, and this is very similar to the pigeonhole argument you were doing a few moments ago, is I've got to place 3 points. 2 points have to be in either the outer or 2 points in the inner. 1 gets at least 2 of 3, and we win. So we just keep pigeonholing it to death. So I think we could also try to draw a great circle with these 2 points going through the center that's going to cut things. It's essentially similar to what we're doing here, and I've just oriented it so that the great circle is just the natural one over there. We could have actually put them on the equator, and that might have been a better choice to do because we have a word for this, equator. And then we have northern hemisphere, southern hemisphere, rather than inner hemisphere, outer hemisphere. So if I were to redo this problem, if I were to write this up nicely, I would probably put them on the equator and use different terminology. The idea, though, is similar. So the question is now, let's just go back. We've got like a minute or 2. Did looking at 2 dimensions help us? Or did the proof we come up here, was that more specialized than we needed? I mean, if you look at it in hindsight, we're saying is we do have to choose 2 points in here by the pigeonhole. We have, we've chosen 2 points here. We have to add on 2 more. Is this being done by a pigeonhole? I don't quite see the pigeonhole here. What we could have done is we could have chosen just this 1 point and then said we have to add 2 out of 3, and either 2 on this side or 2 on that side. So this is not a great, this proof doesn't really generalize as well. Doesn't generalize as well as the pure pigeonhole, as the pure pigeon. There's still, in some sense, a forcing going in. But it's not quite the pigeonhole. It's this, they have to be down here in this part. So it is absolutely possible to be misled by looking at lower dimensional cases, because you may use extra things about that property, about that space, that do not necessarily hold higher on, or there might be an easier proof in that case that doesn't generalize as well, or maybe this does generalize. And maybe there's a good way of us to put this down with slices, which is how I was originally looking at things. But the pigeonhole, I think, is a little cleaner. So there's a lot of great lessons from this problem. And we did this in about 50 minutes, which is, if you consider how much time you have on the Putnam, if you can solve 1 problem every 50 minutes, you're doing great. Usually, it's not a function of time. So I really want you to think about this problem and the different ways of attacking it. You do some Googling, see if this has been done before, see what you think the answer might be as we try to go higher and higher and higher for spheres. Uh-oh, Munchkin's coming. Was that someone's phone? All right. So any other questions on this?
I mean, how would you, how would you even approach going into higher dimensions?
Formally. And so I would no longer try to be drawing these pictures, because these pictures are already bad enough for me at the level 3. but to just say formally, I choose one point and it's going to split into two spaces. And I can keep playing these games.
I guess my question is like, so in the 2D case, we can assume a maximum of 1 point lies on the border, like guaranteed, and then in
Correct.
3D we can assume that 2 points, maximum 2 points, always lie on the border because you can form a circumference.
Right.
Can you?
Right, so that could be another interesting question as to, in these configurations, how many points can you have on the boundary? Because they said it's a closed hemisphere, not an open hemisphere. It's very important that you contain that last extra piece. So there's a lot of great questions you can ask. It's a really nice Putnam problem. Not all the Putnam problems are like